Physics, Kinematics, Chapter 2 in our book, Uniform Acceleration. This is a summary. We're going to boil everything down to three basic equations. There are more equations, more detailed equations, but for us these will be the three equations with some of their variations that we will stick to or limit ourselves to in this unit. First of all, we've had the definition of average velocity, which is V average is displacement, which we're using a D for, over time, displacement over time. If you plug in distance there, you will get the average speed. Okay, average acceleration. The definition is delta V over T. But usually that equation will be written like this. For any delta or change in anything, it's the final reading or final velocity, V sub f, which would be an instantaneous velocity, not an average velocity, minus the initial velocity, V sub I, over t, time. That's the equation that we'll be typically using for average velocity. Average acceleration. Once again, velocity is in meters per second. The standard units for acceleration will be meters per second squared. Finally, we have the new equation. The distance or displacement during a period of acceleration is 1/2 times a times t squared. So that'll be our third equation. Those three equations that are circled, you can do every problem with those three equations. Now some variations. I have this set up over here on the left. You can use some algebra there, multiply both sides by t, and equation number 1, or the average velocity equation, would turn into d equals v average times t. That's just a reformulation or a rewriting of that equation. So it's not a new equation, but you'll see that written in some books, that d, displacement, equals the average velocity times the time. If you take the average speed times the time, you get the distance. Furthermore, in the middle column here, a lot of problems will have an object that starts accelerating from rest. And by the way, I forgot to mention this as well. Over here on the right-hand side, very, very important, this last equation only works if you are starting from rest. That last equation. The other equations that I have on here will work whether you're starting from rest or not. They're just overall averages. However, one more thing here in the middle column. If you do start from rest, that means V sub I is 0. So the middle equation can be simplified, so you'll see this in some books or some situations, that the average acceleration will just be V sub f over t, because if V sub I is 0, that's what you have, V sub f minus 0. It's just V sub f over t. But it's usually not written like that. Usually that equation right there is rewritten as such. It's written like this. I'll go over this way. As solve for V sub f, and you get V sub f equals a t. So you might see that equation. But I'm going to stick with the three that are in the circles here. Keeping in mind the one in the upper right hand corner, the displacement, that equation only works, d equals 1/2 at squared, only works if you start from rest. There's another equation you could use that factors in an initial starting velocity. We're not going to do that in these problems. I'm going to show you that all the problems we're going to be doing can be solved with one of these three equations or a combination of them. Once again, also a note for vectors down here. The vectors, when you're doing vector problems, you do have to keep track of the negatives. With the distance problems, never plug in any negatives. I'll give you some examples here in a little bit. So here are a couple of examples. And there are some shortcuts you can take. For example, in number 1, you're dropping an object and you're letting it fall for 7 seconds, and we want the average speed for the 7-second period. Now here would be the long way to do that. You would use the acceleration equation. Let me just preface this by saying, if you've thought about this long enough in regards to the problems you've already done, you know that if it falls for 7 seconds and we round off the acceleration due to gravity at 10 meters per second squared, this ball's instantaneous velocity after 7 seconds will be 70 meters per second. Let's just take that shortcut this time. So the ball picks up a speed of 10 meters per second each second, a velocity of -10, but this one's just looking for the speed. We know that after 7 seconds, just from doing enough of these problems already, that in 7 seconds worth of fall, the ball will have a speed of 70 meters per second, a velocity of negative 70. That means if it started from rest, which it did, it starts at 0 meters per second, its average speed, speeding up from 0 to 70, is just the average of 0 and 70, or the number halfway between 0 and 70. So the average speed, which I'll symbolize with V average, the average velocity will be negative 35, but the average speed will be just 35 meters per second. So that's the easy way to do part one. Let's not do that one the hard way. Just do that conceptually. All right, that's the average speed for that 7-second time period. Now, part B, I am going to do this two different ways. If you look back at those equations, the two equations are, or the one in particular that's the newest, d, or displacement or distance, equals 1/2 at squared. If you start from rest. Is this object starting from rest? And yes, it is starting from rest. Therefore, we can use that equation. We don't even need part A. We just plug in straight up to get the displacement or distance if we don't factor in the negatives. I'll comment more on that in a second. But gravity's acceleration is 10 meters per second squared. You could plug in 9.8 if you want to be a little bit more precise, but times 7 quantity squared. All right, so you just work that all out on your calculator. 7 squared is 49, times 10 is 490. Half of 490 is, I believe, 245. So it will fall 245 meters. That's the distance. The displacement would be negative 245 if they asked you for the displacement, but they only asked you for the distance here. So the answer there is 245 meters. But let me show you one more thing. If you look back at the equations from the previous page, we can also do this problem, and you don't need to do these problems two different ways, but the distance can also be calculated by taking V average times the time. Plug in the average speed to get the distance, plug in the average velocity to get the displacement. Well, here we see that the average velocity from part A is 35. Check this out. This is kind of cool. Times 7, which is a quite a different looking equation there than the one at the top here, d equals 1/2 at squared. But indeed, if you take 7 times 35, you do get that d, the distance, is 245 meters. That has to be consistent. It is the same answer. If it's not the same answer, we have a problem. Just another way to do the problem. You don't need to do it both ways. Okay, number 2 here. An object traveling with a velocity of 30 meters per second accelerates for 6 seconds. Calculate the velocity at the end of the 6 seconds. Now, it's implied in part A here that we're trying to get the instantaneous velocity at the end of the 6 seconds. Well, this is fairly classic, straightforward in the sense of plugging into the average acceleration equation, that the A average is V sub f minus V sub I over t. Once again, I want to show you that basically every problem we can do, we can do it with one of the 3 equations that I circled on the previous page. In this problem, it tells me that the acceleration is 4. Check the units first, make sure we're good with the units. If not, we've got to get them all in a standard form, which these are. So the average acceleration here is 4, which is constant at 4. V final, we don't know what that is. We're looking for V final, the final velocity, the instantaneous velocity at the end. But V initial here is 30 meters per second. So that's V final minus 30 over a time of 6 seconds. So now it requires us to do some algebra. So I'm going to multiply both sides by 6, and I'll start working back up here just to have some space. 6 times 4 is 24, so I get 24 equals V sub f minus 30. And then I add 30 to both sides, I get V sub f equals 54 meters per second, because that will be standard. That's my final velocity, instantaneous velocity at the end of the period. Now, once again, the shortcut would have been one of those equations that was an offshoot of the 3 that I circled. If you want to take the shortcut, because V sub I, actually you really can't take much of a shortcut here. we pretty much have to do this problem this way with the constraints that I've given you with those equations, because we did not start with a v initial of 0. So this is the way you're going to have to do this particular problem. There's some conceptual things you can think about, or you could draw a chart, I guess would be another way if you drew a chart to show your work, that if you start at 30 meters per second and you're gaining 4 meters per second each second, for example, after 1 second's worth of time, this car or object would have been at 34 meters per second. That's adding 4 onto the 30. And then after 2 seconds, you add another 4 on. That would be 38 meters per second. Keep adding 4s for 6 repetitions, 6 seconds, you would get to the 54 as well. All right, but part B here, the distance traveled during the 6 seconds. So in part B, let's see if I can squeeze it in here. Part B, all right, it says find the distance traveled. Now, the equation d equals 1/2 at squared assumes you start from rest, so you cannot use that equation in this particular problem. So what we do need to use in this problem is v average equals distance over time, or displacement over time. I'm going to go to the next page to finish this problem off. All right, so I'm showing you once again that you can use the 3 circled equations on page 1 to do all problems. The v average here, do some thinking, some conceptual thinking. If the car or object started at 30 meters per second, which it did, it ended at 54 meters per second, that was v final. What is the average velocity? Well, it's the number halfway in between those, or basically just take 30 plus 54, which is 84, divide by 2, that's 42. So v average is 42 meters per second. The car didn't stay at any particular speed, it sped up. It averaged 42 meters per second. So we can just plug that into v average, 42. This is really the only way we have right now to figure out the distance for an object that did not start from rest. You have to do it this way. The distance will be unknown. And what was the time? 7 seconds. So, no, it was 6 seconds. It was 6 seconds. So the distance traveled will be 6 times 42, which is 252 meters. That's how far this car would have traveled during that time period. It's the average velocity times the time. All right, and finally, example number 3. Snoopy's running 84 meters in 7 seconds. If he maintains this pace, how far does he travel in 12 minutes? All right, well, the first thing we can do here is figure out his average speed, average velocity. Once again, when all else fails, try all 3 equations, but after you've done enough of these, you know that the first one on the first page is the one to start with. This is going to be a 2-step problem. That's what makes it maybe one level more difficult than some of the other ones. But my v average is my distance traveled in the time given. So here we have the average velocity, or average speed actually. We don't know if he goes in a straight line, but we know his distance is 84 meters in 7 seconds. Once again, double check your units there, make sure those are appropriate, and they are meters and seconds. So my average velocity here is, I believe, 12 meters per second. Well, that's Snoopy's average velocity. All right, then it says if he maintains that for 12 minutes, how far does he go? So basically, we have to we have to reuse that equation again with a different time. So I'll just write it down generically again. V average is the distance over time. If he maintains that speed, in other words 12 meters per second, what distance does he travel if the time is 12 minutes? But be careful here, 12 minutes, we want seconds. So we have to convert that into seconds. Basically take 12 times 60, which is 720? 720 seconds. Because 12 times 60, 10 times 60 is 600, plus 120. All right, now we got to get the distance. So it's going to be 12 times 720. 10 times 720 is 7,200. Let me pause for a second and get the answer, just to make sure. All right, that was 8,640 meters. 8,640 meters, which is over 8 kilometers, which, what would that be, 5-ish miles? That's pretty good in 12 minutes. That's very good. Anyways, that's the distance that Snoopy traveled maintaining that pace.